Question 13. We got digital signals, and it's saying it's 1 volt when it's on, 0 volts when it's off. It changes every second. Draw what you get. Well, if it's on, it's at 1 volt. It changes every second, so after 1 second, what's going on? It's off. So there we go, down there. And it's off, and it's on again. And it's on for a second, then it's off again. And we don't know any more than that. So no curves, triangular waves, anything like that. It's on or it's off. Which of these processes occurs in an analog to digital converter? So analog, things like recording sound, displaying it, not necessarily. Randomizing, just changing the order of it. Sampling, that's going to be our answer. Storing it, well, if we got this and we stored it like that, it wouldn't be any different. So it's sampling. Imagine getting sound waves and turning them into a digital signal. An optical fibre is made of glass, and the speed of red light in air is 3 times 10 to the 8, and in glass it's slower, 2 times 10 to the 8. And there's our refraction. Calculate the angle of refraction. Well, in the back you've got these equations again, and we've got this is what we need for this particular one. So let's just write that down. So we've got refractive index is speed of light in air divided by the speed of light in the medium. And so, but also we've got, I'm just going to separate this. We've got refractive index is our other sine I, which is the angle of incidence, which is there, divided by sine r, which is our bottom one there. So we've got two things there. So sine I, we know that. R, we don't know. N, well, we've got C and V. So that's C and that's V. So we can work out N. So N is C divided by V, so 3.0 times by 10 to the 8 divided by 2.0 times 10 to the 8. You don't really need the 10 to the 8, so 3 divided by 2, 1.5. So N is 1.5. So now I'm going to rearrange this equation. Let's just separate that. So I want R on its own. So I'm going to times both sides by sine R. So N sine R equals sine I. And then we can get rid of this N by dividing by both sides, equals sine I divided by N. So we've just worked out what N is, 1.5. Sine I, what's I? So I is 30, so sine 30. So sine I is sine 30. So sine 30 half, or 0.5 divided by 1.5, so sine R equals 0.5 divided by 1.5, which is 0.333, whatever. Okay, and now we just need to go we do kind of need to do reverse sine. So where's that? That's shift. This sine -1. Put our 0.3s in. And that gives us R equals 19.47. And that's our answer there. So 3 marks there. You can get intermediate marks along there for doing a few things right. But that's what you need. And part D, strengths and weaknesses of using optical fibres. All sorts of things you can say here. I'm just going to summarize some of them. So, optical fibres to supply broadband. So remember, optical fibres, they can go around corners. We have got our signal being totally internally reflected and so on, but it means it can go around corners. And total internal reflection, so we're not losing any of our signal outside of the fibre. So strengths. So can carry more information. So signals can carry more information because the word is multiplexed, but multiple channels can be used. Multiple channels can be used, so different frequencies. Now these are different frequencies. A little bit tricky that. Signals are resistant to hacking because these can be encrypted and be more secure. So signals more resistant to hacking, can be encrypted. It's very hard to break the cable without being detected. Hard, because the person at the receiving end would know that there's some sort of problem. Hard to break the cable undetected. One of the main benefits is with these sorts of digital signals, optical fibers and digital signals, is that you could have a detector that regenerates the signal. So you can stop any degradation of the signal. Just like a CD where you can copy it as many times as you like, the information will be retained. So signal can be regenerated, so no loss and greater distances. Along those very same lines, it's less susceptible to interference, so less, so let's say, affected by interference. it's hard to interfere with a light signal. If you've got kind of electrical sources nearby, it doesn't affect it as much as some other signals might do. E.g. electrical noise. So that means you get better quality. So better quality signal. You've got a good range of frequencies, so better broadband rate, so greater range of frequencies. So your broadband rate is higher, so high broadband rate. Remember, this is just for 6 marks, so you just need any 6 of these will do. Data can be used directly. Because most devices are digital. You don't really need to convert any of these signals at the device, so no loss of data at the device. So there's usually no interface or conversion. And going back to this diagram again, because of this totally internal reflection, you get very little loss of energy. So little loss of energy as total internal reflection. So that's the strengths. Let's see if we can come up with some weaknesses. Well, currently digital signals use a greater bandwidth than analog signals, so more channels are needed, so not quite as efficient sometimes. Maybe we'll come back to that one. Let's go back to this fibre again. Well, it could be, because it's glass, it could be brittle and it could break. So there's a more obvious point. So fibres easily damaged because they are brittle. Repairing them and joining them is difficult. Joining or repair of optical fibres is difficult, so need a specialist, or it might be expensive. And if you get kind of poor joins, imagine 2 cables not quite put together right, you're going to get poor signal. Leads to poor signal. There are a couple of other points, but probably leave that there. You need 6 points from those. You can look at the mark scheme and really you just need to learn advantages and disadvantages for all these different types of radiation and used in communication. It's a lot of learning so that you can repeat them.